All right, so joining us virtually, I'd like to introduce you to Christopher Drake. He's a lead mathematical statistician in Army Futures Command at Picatinny Arsenal. As part of the Systems Engineering Directorate, Mr. Drake has over 10 years of experience working on highly complex research and development programs as a statistician in the Army. He also has more than 10 years of experience as a lecturer for probability and statistics courses for the Armament Graduate School, a graduate school at Picatinny Arsenal, offering advanced degrees in specialized areas of armaments engineering, if you're interested. Mr. Drake gained his bachelor's degree in industrial engineering from Penn State University with a focus on manufacturing systems, and his master's degree in applied statistics from the New Jersey Institute of Technology. All right, take it away, Christopher.
All right, thanks for the introduction. Can you guys hear me?
Yes.
Okay, great. All right, so you can see my screen on the right, correct? And it's just a data table. Let me try going into presentation mode here. Can you now see the presentation?
Yes.
All right, cool. So yeah, the introduction covered my background. I was supposed to be there in person today. Unfortunately, the travel restrictions had other plans for me. But hopefully this gets through okay and we avoid technical difficulties. So the program here that I was working on, I developed a statistical batch weighing methodology to help this program who needed a better solution to a problem. And we're going to go into that summary here in the next couple of slides. So the agenda, we're just going to talk about the summary and motivation. Then we'll talk more about the statistical methodology detail, and then we'll talk about the case study. The case study is fully desensitized. This was a sensitive program, so I've completely anonymized the data, but it should still get the point across just fine. The interpretation and guidelines, then next. Remedial methods if you have excessive misclassification after you've done all this, and then some conclusions and what I hope to work on in the future on this, because this is one project of many I'm working on. So, batch weighing, what we're talking about here in manufacturing or research and development environment, oftentimes batch weighing is utilized to gain efficiencies and save money when you're routing many homogeneous parts. You avoid the need to hand count these parts individually, and counting machinery can be very expensive. So you still maintain rough visibility on batch weighing, but the problem is it's very hard to be precise in knowing what your misclassification risks are when sending batches, meaning how can you be sure that it's the desired number of parts based on that weight. And so when parts are sensitive, critical, or you just wish to be more precise with the counts in the batches, we really needed a more rigorous statistical approach than what we were using here. And so reliable counting machinery can be an option, but it's expensive, and often it's actually not as reliable as you hope. Hand counting parts is obviously time consuming, and it's actually quite prone to human error. And so the methodology that we developed to help solve this problem is a rigorous and flexible statistical approach where we're basically using a Monte Carlo simulation to set up the analysis, and then linear discriminant analysis to give us the model that gives us a holistic look at the misclassification probabilities. And so the problem statement in a concise way would be that there currently exists no statistically rigorous methodology to specifically assess a batch weighing feasibility for any given situation, the misclassification risks that there might be in that batch weighing operation, and then giving the users a quantitative weight limit option that they could aim to meet their needs. The objective and deliverable I was tasked with here was give the users ability to determine the probability that any batch contains n number of parts given an input batch weight, and then also provide those users with an upper lower weight limit so that they can just add parts to the scale until it got into that weight limit, and then they should be confident, given their acceptable risk levels, that the number of parts that they want are in that batch. So the motivation here, the team I was working with, this is a research and development operation. They're trying to route certain projectiles internally, and they were having issues with those deliveries, having extra unaccounted for parts. And they were sending 1,000 parts at a time. And due to the sensitive nature of this program, that was an issue. And so they tried incorporating a laser counting system, which was actually making things worse somehow. It was consistently having problems. So they had to go to hand counting, unfortunately, which has obviously increased the man hours and the inefficiency. And created a new bottleneck there with the counting of the parts. And so the team contacted me, trying to help them, bring back batch weighing in a way that was transparent and we can understand the risks and move forward that way. And so using a recent robust set of weight data for the individual parts, we were able to help develop this methodology. So here's a little bit of the detail here. So just, I know that one of the presenters isn't presenting today, but if you need me to speed up, just give me a kick because I have a lot of material to get through here. So I'll do my best to go fast. So the detail here, this is basically a flow of how I thought to solve this problem. So my screen keeps going in and out. Can you guys see that? Okay,
Yes.
there we go. So conceptually, to quantify this misclassification risk, we basically need distributions of batch sum weights to be assessed holistically on the axis of interest. And so in order to do this, it's a real testament to the power of Monte Carlo simulation because we're able to do all of this with really just an estimate of mean and standard deviation. From here, we can develop all of this following that. So Monte Carlo simulation is used to generate individual part weight distributions, and these are normal distributions, using the parameters from that robust set of data that we gathered on those projectiles. And you don't have to have that data. You can use subject matter expertise, but obviously you'd prefer to have recent robust data. So then from here, we're considering the worst case misclassification scenarios, which would be that you have one extra part or one fewer part in that batch. If you have 10 extra parts or 10 fewer parts, the signal is going to be quite large. It should be pretty obvious on your scale that something's amiss. But if there's one fewer or one more, it might get lost in the noise. And so we're trying to assess here based on this data, can we even batch weigh in a way that we can be sure that we're sending the correct quantity? Or are we just going to have to be stuck with, losing one or two here and there just due to the noise? So Monte Carlo simulation is then used to generate column sums, excuse me, of batch weight sums, basically, of size n-1 and n+1 parts. That data is then stacked into one column, and we apply the linear discriminant analysis model, supervised machine learning model. And then those outputs can be used to estimate probabilities of misclassification of each individual batch. And then I've developed a very simple formula here. If you want to do a more macro view and assess the misclassification probability over the lifetime of a program, so multiple batches in sequence because the problem kind of compounds, unfortunately. So then I have some remedial measures proposed if the misclassification risks are too large, and we'll get to those. This is a flow chart of basically what I just said for the more visual learners out there. This is in the paper. I plan on submitting this to the manuscript in May, so this will all be in the paper. I've done this whole analysis with JUMP, by the way. So yeah, I'm not going to detail that because it's pretty much the same as the other slide. So a little bit of detail about LDA. LDA is a pretty popular supervised machine learning classification model-based approach. And so it turned out to be pretty much perfect for this method. And so, we're able to combine these two known statistical tools and give us a nice structured methodology for batch weight misclassification. So in essence, with LDA, is you're calculating a statistical distance for each observation from the class means. In this case, we have 3 class means. We have that n+1 and n-1 group. And so the output of this model is going to give us probability of class membership for each point, and that's going to be a batch weight. And the output is also a confusion matrix of misclassification rates, which is really nice because we're able to separate that into type 1 and type 2 error. So one limitation of LDA is there are some assumptions, normality and homoscedasticity being the main ones. That being said, I do believe you can get reasonable results if your data is non-normal, something like log normal, for example. There are some robust LDA options out there. I've cited a couple. And so I do believe that this wouldn't necessarily be limited to purely normal applications, but in this case, it was normal. So we didn't have any of that issue. So here's a diagram of the different misclassification types here. So the null hypothesis is that we're shipping 1,000 parts, and the alternative hypothesis is that we're not. And obviously, the the biggest issue here is a false negative where we're getting an escapement. We're basically predicting that the batch contains 1,000 parts, but it does not contain 1,000 parts. And this is what we've been trying to avoid in this program due to the sensitive nature of the program. The type 1 error is also bad and can lead to problems, but when you're saying it does not contain 1,000 parts, but it actually does, you're not going to ship that batch right away. You're probably going to hand count it or take a deeper look at it before you send it out. So the one that we're mainly considering is the type 2 error, but we'd like to avoid both. A couple considerations before I get into more of the details of the case study. Measurement systems are very important when you're applying this methodology. It's very important to understand your measurement systems. We're talking about things like repeatability, reproducibility, bias, linearity, the maximum capacity of the scale, resolution of the scale, or readability. All these things are important to understand. If you have no idea about your scales and measurement systems before you're doing this, I don't recommend applying this. And the same can be said for your process. If you don't have a stable process yet, you can still apply this. As we're going to talk about, there's some correction factor options if you have process drift, but preferably a stable process where the measurement system is well understood. So you're going to be hopefully using the same scale to take the individual part measurement data that you base your Monte Carlo simulation off of and the batch weight data that you're going to be collecting in the future. But if not, you can just make sure using gauge R&R that those two scales aren't wildly different from one another in terms of their repeatability and things like that. So this is kind of a warning slide, I'd say. So without a well-understood measurement system, you might suffer some irregularities when verifying this model approach with real-world data as it comes in. The next warning slide, I would say, is continual process monitoring is key here because you're basing this whole analysis off of an estimate of mean and standard deviation. And as lots come in, there could be process drift. There's lot-to-lot differences in means and standard deviations. So we need to be making sure those things are understood and accounted for. The good news is there's usually solutions for these things. So if a new lot comes in and you see that the mean is off by a certain amount from the Monte Carlo simulation mean, you can usually just apply a simple correction factor to adjust for that. If the standard deviations are different, let's say the standard deviation is smaller, shouldn't be an issue because it's just a more conservative outlook now. If the standard deviation is larger for this new lot that comes in, then you might need to just rerun this analysis and rerun the Monte Carlo with that new larger SD just to make sure you've accounted for that extra noise. So continual process monitoring before you do the actual batch weighing is key. All right, now we'll get into the case study setup here. Again, this is fake data. We're using parts that are 1 gram with standard deviation of 0.007 grams, batch sizes of 1,000. And so as I mentioned, in an attempt to understand this whole atmosphere here, we need to look at the +1 and -1 situation. So here you see, let me get my laser pointer here. So in this column, you have the Monte Carlo simulated individual parts. And then here you have an example for the 999 batch. And you can see it's just, the mean is gonna be roughly 999, right? Because they're 1 gram parts. And so when you sum 1,000 of those, or sorry, when you sum 999 of those, you're gonna get a distribution centered on 999. And so we're gonna do the same thing for 1,000 and 1,001. And we're gonna do that 10,000 times. I tried to do larger, but my computer was running out of memory. You could do larger if you want on an HPC or something like that. But you're gonna have hundreds of millions of rows to do this like I did in JUMP. There could be other ways to do it in Python. But to do it this way, 10,000 was plenty. I wouldn't recommend going too much lower just due to the resolution. But this was good for our purposes. So that was for the setup of the individual parts and the sums. So here I've walked through exactly all the detail on how I did this. I'm not going to go through it word for word here, but if you're a JUMP user and this interests you, a lot of the details here. And so essentially what we're doing here is now we're lining up the sums of the batch weights, right? So we have our 999 batch, our 1,000 batch, and our 1,001 batch. And we're really trying to see how much overlap there is just on first glance. Right now, it looks like there's some overlap. It doesn't look overwhelming, but there definitely is overlap. But sometimes these distributions can be spread quite far apart, and that's good, right? You don't want there to be overlap for the success of this, but if there is, that's okay. So here I've just, using integration, we see that the overlap is about 0.0472. That makes visual sense. From there, we're going to take these three distributions and stack them into one column so that we can apply our LDA analysis. Okay. So this is a normal three mixture that we're going to be looking at here. Excuse me. So here we have the LDA model fit. This is the profiler tool, which I'll open here in a second and show you what it looks like. But when interpreting this model, we're going to be looking at a few things. One, the overall misclassification, which you can see here. This is based on the confusion matrix and the actual data. So I've actually simulated 1 million batch sums for each weight, basically. And this is our confusion matrix. So we're going to be looking at overall misclassification, type 1 and type 2 separately if you want. Type 2 because that's our worst case scenarios of particular interest. Probability of class membership is going to be given by the model. And misclassification given weight limits. So we're going to be establishing those weight limits in the next couple slides. That just makes it easier for the users to apply this methodology. And then misclassification over multiple batches. That's if you're going to be doing this many times and you want to see what's the chance that we have an escapement over the life of this program. So as I mentioned, the least desirable outcome is that type 2 error. So we're going to be paying attention to that. But let me close this and show you. Can you guys see this now? Are you guys able to see this screen?
Yes.
Yes.
Okay, cool. So this is the jump output for the LDA. And this is what the profiler looks like. Super useful tool. I don't know if you guys are familiar with ordinal logistic regression, but it looks a lot like that. And so basically what this is saying here, our x-axis is the batch weight. As we input batch weight, right, we're changing this now. This is basically saying that the probability that this batch contains 999 parts is almost 100%. As we move up in the weight, you're going to see we're now getting into a confusing area where it's going to be about 50-50 at some point where we're not sure if it's 1,000 parts or 999. And then as we increase the weight, now it's almost fully 1,000, right? And then we go to the 1,001. So this is a really perfect look at our misclassification probabilities given all of this input, which is really, really nice. All right, I'll go back into the slides here. Another nice thing about this, so if we want to, just to look at why our overlap isn't perfectly lining up with our misclassification. So I've also able to overlay the probability density function of that normal three mixture in the same profiler tool, which is kind of cool because you can see that the areas that are the most confusing to the model, this kind of 50-50 area, let me get my laser pointer back, this kind of 50-50 area for both of these transitions is actually lined up with the least likely weights, which is nice. That's kind of why we see when the overlap is this number, but the actual misclassification percentage is lower. So we're kind of benefiting from this combination of probabilities. So identifying upper and lower weight bounds. Why do we want to do this? So the users are basically, they want this model, they want to be able to type in a weight and then know what the probability is that it belongs to the batch size that they want, but they also wanted a more user-friendly way where I can just give them weight limits and say, just add parts or subtract parts from the scale until you get between this window. If you get in this window, you can be X confident that that batch contains 1,000 parts. Okay, that's kind of the solution they wanted. And so we're able to do that with this model. So we basically output the model here in graphical form. And we're going to line, in this case, I've just used a 5% total misclassification acceptable risk level. So 2.5% in each tail. We're going to look at the 97.5 point here to get the upper limit. And then we go down here and look at the lower limit and we get 999,681 and 1,321. And so we're able to give those now to the user. Again, they're going to add or subtract parts until they get in that window. If they can't get in that window, they're probably going to have to hand count because now there's some ambiguity and we're kind of lost in the noise. Because we're stacking so many parts, that noise can get, it can be cumbersome as you stack more parts. So once we apply these weights to the distribution here of the 1,000 sums, we can see that about 15% are outside those. So they approximately 15% of the time, they may need to hand count just to mitigate the risk. Moving on from there, if you want to take a more macro approach here to evaluate this problem and assess it over the lifetime of the program, there's a very simple formula here where we're basically we're having compounding issues here where you're going to do this batch after batch after batch. So what is the risk over the program that we're going to have an escape or more? And so if we define that acceptable risk level as 5% over the life of the program, we can just input an approximate number of times we're going to be batch weighing. In this case, it's 100. And then here's our acceptable risk level. And this is going to tell us that our type 2 risk per batch can be this or less to satisfy this particular program. And so when we take this back to the actual stacked data, the normal 3 mixture, we can then solve to get these limits, which is going to give us our type 2 error here. So in this case, we've got these limits on here. Most of them are 1,000, but there's going to be some small subset that are 999 and some small subset that are 1,001. That's going to be our type 2 error when we sum those. And here in this case, we've just met it, right? So we're at 0.044, which is less than that 0.05 risk for the life of the program. So this is an alternative way if you want to do it this way. All right, so now we're getting into some remedial methods. So what we just looked at there was some overlap, right? But it was manageable. You can see here that there's much more overlap. So now the overlap calculation is about 85%. Misclassification is around 34 or 35%. And you can see here in the model, we're at perfectly in the middle here at 1,000, right? So our desirability here is maxed on 1,000. And we still have ambiguity with regard to, let me see if I can zoom in. We still have ambiguity with regard to which bin it's in, right? So we're at 1,000, and this model is telling me, I think the probability that it's 1,000 is 52.3%, but it's about a quarter that it could be 99 or 1,001. This is not good, right? So we're going to lose track of parts in this way. So this kind of demonstrates this method's first nice thing is that it can identify situations where you cannot reliably apply batch weighing without losing track of parts. And then this is how we're seeing it. We're not able to do this. Our window is going to be way too small or just non-existent in this case to work with. The good news is there could be some remedial methods that you might be able to take to solve this problem. The first that I'm proposing here is just smaller batch sizes, right? So we're giving the noise less chance to compound over more, basically all the noise stacking that happens over the samples of 1,000. If we decrease that, here I've gone from 1,000 to 50. Here, this graph shows a bunch of different metrics that we're using to assess performance, so overall misclassification, all that kind of stuff. I'm not going to go through all this, but one that I'm referencing here is that we're showing that by going from 1,000 part batches to 500 part batches, we show roughly 30% improvement with overall misclassification. And then when you go from 500 to 250, you see 60% improvement. So there's definitely room for improvement with smaller batch sizes. That being said, there's logistical concerns there. You're also going to have to do more batches. So then you get in that pesky problem where you're compounding that error. But this can be a solution if it's possible to decrease batch sizes. The next option would be binning, where you're taking the 3 distributions and just incorporating them into one distribution. And then you're going to be comparing, in this case, the 2 adjacent combinations, which would be 996 to 998, 1,002 to 1,004. Now, these are going to be our 3 distributions, and we're going to do the same exact methodology and LDA to this and these 3 distributions. The obvious problem here is you're going to lose precise count on the parts. This could be okay, though, if the application isn't like mine, where it's super sensitive. This still allows you to have a nice model-based approach when maybe the parts are just simple widgets. You're losing track of toothbrushes. It's not a big deal. We're losing track of sensitive projectiles. It's much more of a concern. So this could be an option for less sensitive programs.
Hey, Chris, sorry to interrupt. You have 5 minutes left.
All right, we're almost there. The last remedial method is just a combination of both. So you can do a little bit of both here. You can shrink the batch size from 1,000 to 500 and then also apply binning. And in this way, we've gotten a 75% improvement to the overall misclassification. And here's just a table of the improvements based on several remedial methods that I've tried for your reference. So conclusions. I'll just read this last line here. So successful application of this methodology, coupled with continuous process monitoring and understanding your measurement system, will result in less misclassification error and more confidence when implementing batch weighing, while still saving precious time and money. And so this actually did end up getting implemented recently, and so far the few attempts we've gone through to apply this have been successful, and they've been 1,000 parts on the dot, and so far it's been great. And over the long run, you're going to experience times where it's not 1,000 parts, but we're still experiencing a bigger improvement than losing 1 or 2 with the laser system that we were. So far, so good. Future work, looking at researching possible extensions other than just batch weighing, where noise stacking and misclassification rates are a concern. And then also looking to explore the consistency of some of these remedial methods, if there are some governing underlying truths that are basically that are governing the magnitudes of the improvements. So I want to see if I can find there's underlying truths to those improvements. And then going into more detail on the correction factor, just to give users a specific structured approach for that correction factor when there is process drift observed. Here's some references for the robust LDAs and some more on LDA. And here is a jump script for that overlap calculation if you're a jump user and that interests you. Yeah, and I'll leave it there. This is my contact information if this, hopefully this can be applied for some of you. But if you're interested, you can reach out to me and I'll help you along with that. So thank you.